Hello everyone, my name is Duc and I am a PSRS student. Today I'm going to talk about my internship topic, surface enhanced Raman spectroscopy by metallic nanoparticles. Currently, I'm working as a research trainee at VTT Technical Research Center, Finland. My internship topic is surface enhanced Raman spectroscopy with metallic nanoparticles. So in this presentation, I will present the principle of the search self-active configuration with FPTD simulation, search measurement with polystyrene with different size of gold nanoparticles in order to find the optimized diameters of the gold nanospheres for the best search enhancement. So first, what is the surface enhanced Raman spectroscopy? So the search is based on the principle of the localized surface plasmon. If we have a nanoparticle smaller than the wavelength, we can consider the electric field is uniform around the nanoparticles. The oscillation, the electric field drives the electron cloud move back and forth, and the oscillation of the electric cloud radiates the secondary wave coherent with the incident light, and this phenomenon is called the localized surface plasmon. So let's take a look at FPGA simulation here. We can see a very strong enhancement in the surface, and this is called hotspot. If we have a molecule in this area, it will be excited and radiate the Raman scattering. The Raman scattering again will be enhanced in the same principle of localized surface plasmon here. And finally, we have the intensity of the source proportional to G prime G to power 2, where G is the gain factor of the incident light and G prime is the gain factor of the Raman scattering. Because the Raman shift is small, so we can consider G prime equal to G. And finally, we have the enhancement factor EF proportional to G to power 4. So in this work, I use the focal Raman microscopy. It works at 540 nanometer. The laser excites the sample, and the Rayleigh scattering and Raman scattering will be collected by the objective and focusing by the focusing length here. Before entering the spectrometer, the field will be filtered by the notch filter here to prevent the Rayleigh scattering, and the Raman scattering will be analyzed by the CCD. So in order to repair the surf active measurements, I have the polystyrene bit coated with biotin and the gold nanoparticle coated with streptavidin, because the biotin and streptavidin, they have a very strong bound. So that's why I can conjugate the polystyrene with the gold nanoparticles like this. So here is the FPTD simulation of this configuration. So we can see here, this is the polystyrene bit and the gold nanoparticle. We can see a very strong enhanced here in the interface between the gold nanoparticle and the polystyrene. So in the result, I did the FPTD simulation with the different size of gold nanoparticles from 10 to 100 nanometer, and vertical axis is the gain factor of the excitation wavelength. We can see here the resonance is at 60 nanometer, which gives the highest gain factor. So in figure 7 is the Raman spectra of polystyrene with different size of gold nanosphere that I measure with the confocal Raman microscopy. In this figure, I already subtract the background of the spectrum and shift each spectrum 10,000 for visualization. We can see here at the bottom right is the original Raman without gold nanoparticles, so we can see a very weak signal. However, when we have a gold nanoparticle, is enhance the Raman scattering. So that's why we have a very strong enhancement for 10 and 20 nanometer. Here, the gain factor not very high, so that's why we see a not very strong enhancement. However, for 40, 60, and 80 nanometer, it's due to the resonance, so that's why a very strong enhancement, especially 60 nanometer, give the highest enhancement. So in conclusions, the enhancement factor of the search is the full power of the field enhancement for nanoparticle surface. So for example, if the gain factor equal to 10, so the enhancement will be 10,000 times. It's very huge. So therefore, search plays an important role in the Raman enhancement, which is widely used in sensing application. So in the FPTD simulation, it indicates that the optimized diameter of the localized surface plasmon for the gold nanoparticle spheres at 540 nanometer excitation is around 60 nanometer, and which marks the experimental results. So I will discuss a bit about fluorescence. In Raman scattering, fluorescence is one of the main problems in search. You can see here in figure 8, the blue curve, the original one, because the fluorescence of the sample, so that's why we have a very strong background. So in this figure, I use the algorithm to subtract the background, and the red curve is the corrected one. However, for the sample with a very strong fluorescence, so it will affect a lot. So that's why I use the time gate technology. It appears in this technique. We can see in this figure, in figure 9, after excitation, the Raman scattering will appear immediately. However, fluorescence is shifted a little bit and have a very long lifetime here. So in the time gate technique, so when the time gate is open, it just collect the Raman scattering photon and a little bit fluorescence, and it reject a lot of the fluorescent photon here. So this technique is called a real-time background subtraction. And currently, I'm working with this technique because the biological sample have very strong fluorescence. So that's all. So thank you for your attention. So here are my references. So.
Thank you very much.